Video problem 55, attractive forces in compounds. Predict the order of boiling point for the compounds below based solely on intermolecular forces. So the first thing we have to do is figure out the intermolecular forces. And in order to figure out the intermolecular forces, we have to look at the Lewis structure to determine whether it's polar or nonpolar. So let's do that first. I'm going to do that down here. A lot of these structures we've seen already. So here's CH3Cl. That is polar. We already drew that one. Here's CH4. That dude is nonpolar. Okay. Here's CO2. We know that that is also nonpolar. HF is very polar. Very, very polar. Exhibits hydrogen bonding. H2S looks like this. Looks an awful lot like water. That's going to be polar. And then finally SO2 looks like this. I had to actually pause it to figure this one out. There we go. Okay, and that dude's polar as well. Okay, now what we want to do is figure out what intermolecular forces are present. All right, so CH3Cl, it's polar, it exhibits London dispersion and dipole-dipole. CH4 is nonpolar, so it only exhibits London dispersion. CO2 only exhibits London dispersion because it's nonpolar. HF is polar, it exhibits London dispersion, dipole-dipole, but it also exhibits hydrogen bonding because it has a hydrogen bound to a fluorine. H2S is polar, so it's London dispersion, dipole-dipole, and SO2 is polar, so it's London dispersion, dipole-dipole. Okay, so that's the first thing. So we can sort of put these into categories, all right? So the way that it works is generally, if it only has London dispersion, it's going to have the lowest boiling point, usually, all right? And then we're going to work our way up to hydrogen bonding, which is going to have the highest boiling point, again, usually. Now, when you start to get into much more massive compounds, then London dispersion plays a bigger role, and it sort of throws this off. So I picked certain molecules so this would work. All right, so let's look at just London dispersion molecules. So just London dispersion is going to be CH4 and CO2. So how do I know which one has the lower boiling point between the two? Well, it's the number of electrons. Whichever one has more electrons will have a higher boiling point because the one with more electrons is more polarizable. In other words, it's more likely that it's going to be temporarily polar more often. Think about a room with two people in it, right? You can have two people on one side, two people on the other side, or one on each side, right? So there's 2 out of 3 chances, 66% chance of being polar, right? 2 on one side, 2 on the other side. Now, blow that up to, let's say, 50 people, right? You can have no people on one side, 50 people on the other side, 1 in 49, 2 in 48, 3 in 47, so on and so forth. So there are a lot more chances with more people that it's not going to be evenly distributed. So that's why more electrons means more polarizable. More polarizable means that it's going to have stronger London dispersion forces. It's not always simple to count electrons, so a lot of times to cheat, we look at molar mass. The higher the molar mass, the more electrons. So the molar mass of CO2 is about 44. The molar mass of CH4 is about 16, so that means CO2 has more electrons, therefore it's more polarizable, therefore it's going to have a higher boiling point, right? So if I'm going from lowest boiling point, first I'm going to pick CH4, it's going to have a low boiling point. CO2 is going to be next. Now I go on to London dispersion dipole-dipole. So I've got CH4 or CH3Cl, and I've got H2S, and I've got SO2. So again, now I have 3 of them that are tied with this London dispersion dipole-dipole. I look at the number of electrons. The one that has the most number of electrons is going to have a stronger London dispersion force because it's more polarizable. The electrons are going to be on one side more so than the other. And so it's going to have a higher boiling point. So again, I cheat and I look at molar mass, right? So let's see, that's 35, 36, 37, 38, 50.45. H2S is about 34. SO2 is about 64. Okay, so this one has the most electrons. Ooh, what did I spell there? MOSET. It has the most electrons, all right. This one has the least electrons, and this one has the middlest electrons. All right, so if I'm going to arrange these from lowest boiling point to highest, it's going to go H2S, then it's going to go CH3Cl, and then it's going to go SO2. Okay, so H2S is above CO2 because H2S has London dispersion and dipole-dipole. Right? That dipole-dipole is stronger than just the London dispersion. So now we come to the last one. We only have one with hydrogen bonding. So that's the one that's going to have the highest boiling point. So there you go. You arrange them first based on number of intermolecular forces. Then within the intermolecular forces, you arrange them based on number of electrons. But let me throw this in here. If you're ever given data and the data doesn't match that, then you're probably looking at London dispersion forces as the reason why. Number of electrons, London dispersion forces.